Question 1. Benchmark analysis indicates that a financial services organization is implementing a new IP routing infrastructure and needs to ensure that only authorized internal servers can initiate connections to a critical database server located in a specific subnet. The routing devices at the edge of this subnet are Cisco routers running iOS. The primary goal is to prevent any unauthorized access attempts to the database server while maintaining efficient routing for legitimate traffic. Which of the following approaches best satisfies these requirements within the context of implementing IP routing security? Option A. Implement access control lists, ACL, on the interfaces of the Cisco routers facing the database subnet to permit traffic only from authorized server IP addresses and deny all other traffic. Option B. Replace dynamic routing protocols with static routes for all internal network segments to simplify network management and reduce potential attack vectors. Option C. Configure routing protocol authentication, e.g., MD5 or SHA, for all routing updates exchanged between routers to secure the routing table. Option D. Disable all traffic filtering on the edge routers and rely on the firewall located at the external network perimeter for all access control. Correct answer is A. Implement access control lists, ACL, on the interfaces of the Cisco routers facing the database subnet to permit traffic only from authorized server IP addresses and deny all other traffic. Explanation. Scenario analysis. This scenario presents a common challenge in network design and implementation, where security policies must align with routing protocols to prevent unauthorized access and data exfiltration. The professional must balance the need for efficient routing with the imperative to enforce access controls at the network edge, ensuring compliance with internal security mandates and potentially external data protection regulations. The challenge lies in selecting a routing configuration that is both technically sound for IP routing and robust in its security posture, without introducing vulnerabilities or operational complexities. Correct approach analysis. The correct approach involves leveraging the capabilities of Cisco iOS to implement access control lists, ACL, that filter traffic based on source and destination IP addresses, ports, and protocols, applied to specific interfaces. This aligns with the principles of least privilege and defense in depth, fundamental to network security best practices, and often implicitly or explicitly required by internal IT security policies and general data protection guidelines. By filtering traffic at the ingress point of the network segment, it prevents unauthorized internal or external traffic from propagating further into the network, thereby protecting sensitive resources and maintaining the integrity of the routing domain. This method directly addresses the requirement to control network access and is a standard practice in enterprise network security. Incorrect approaches analysis. One incorrect approach is to rely solely on routing protocol authentication mechanisms like MD5 or SHA. While these secure the routing updates themselves, they do not filter the actual data traffic traversing the network. This leaves the network vulnerable to unauthorized access attempts that do not involve manipulating routing information. Another incorrect approach is to configure static routes for all internal destinations. This is operationally inefficient, difficult to manage in dynamic environments, and does not inherently provide security beyond what is configured on the edge devices. It also bypasses the benefits of dynamic routing protocols for network resilience and scalability. Finally, disabling all access control mechanisms and assuming the network is secure due to internal placement is a critical security failure. It ignores the possibility of internal threats, misconfigurations, or compromised devices, and directly violates the principle of assuming breach and implementing controls accordingly. Professional reasoning. Professionals should approach such scenarios by first understanding the specific security requirements and compliance obligations. This involves consulting security policies, risk assessments, and any relevant regulatory frameworks. The next step is to evaluate the capabilities of the network infrastructure, specifically the routing devices, to implement these security controls. A layered security approach is paramount, where multiple security mechanisms work in concert. For routing and access control, this means combining secure routing protocol configurations with robust traffic filtering at appropriate network boundaries. Decision-making should prioritize solutions that offer granular control, are manageable, and demonstrably reduce the attack surface without negatively impacting network performance or availability. Regular review and auditing of configurations are also essential to maintain security posture. Question 2. The efficiency study reveals that the current IP routing implementation, utilizing IGP, is experiencing prolonged convergence times following network events, leading to intermittent connectivity issues. Which of the following approaches best addresses this challenge while adhering to best practices for network stability and performance? Option A. Disable route dampening entirely to ensure all route updates are processed immediately, regardless of their frequency, and increase IGP hold-down timers to prevent premature route invalidation. Option B. Implement route dampening with carefully tuned parameters to suppress flapping routes, optimize IGP timers for faster convergence without causing instability, and utilize route summarization to reduce the routing table size and update overhead. Option C. Focus solely on upgrading network hardware to higher performance routers and switches, assuming that increased processing power will inherently resolve routing convergence issues. Option D. Increase the IGP hello and hold down timers significantly to reduce the number of routing updates exchanged, thereby minimizing the potential for convergence delays. The correct answer is B. Implement route dampening with carefully tuned parameters to suppress flapping routes, optimize IGP timers for faster convergence without causing instability, and utilize route summarization to reduce the routing table size and update overhead. Explanation. This scenario presents a professional challenge because network engineers are tasked with optimizing routing protocols for performance and stability, but the chosen protocol's inherent limitations can introduce unpredictable behavior. The efficiency study highlights a potential degradation in routing convergence times, which directly impacts network availability and application performance. Careful judgment is required to balance the benefits of a widely adopted protocol with its known weaknesses and to implement mitigation strategies effectively. The correct approach represents best professional practice because it acknowledges the limitations of the chosen routing protocol and proactively addresses them through a combination of configuration best practices and monitoring. Implementing route dampening, judiciously tuning timers, and employing route summarization are all standard techniques to improve stability and reduce the impact of flapping routes. These actions are aligned with general IT best practices for network resilience and performance, which are implicitly expected in professional environments, even without specific regulatory mandates for routing protocol configuration in the U.S. context for this exam. The focus is on maintaining a stable and predictable network, which is a fundamental professional responsibility. An incorrect approach that involves disabling route dampening without a thorough understanding of the network's stability characteristics is professionally unacceptable. Route dampening is a mechanism designed to prevent rapid route flapping from destabilizing the network. Disabling it without a clear justification and mitigation plan can lead to increased routing instability, network outages, and service disruptions. This demonstrates a lack of due diligence and a failure to adhere to principles of network stability. Another incorrect approach, such as increasing the hold-down timers significantly without considering convergence impact, is also professionally unsound. While longer timers might reduce the frequency of updates, they can drastically increase convergence times after a network change or failure. This directly contradicts the goal of an efficiency study aimed at improving performance and can lead to prolonged periods of network unavailability, impacting business operations. This shows a misunderstanding of the trade-offs involved in timer tuning. Finally, an approach that focuses solely on hardware upgrades without addressing the underlying protocol configuration issues is a misallocation of resources and professionally inefficient. While hardware can play a role in network performance, if the routing protocol is misconfigured or inherently unstable, hardware upgrades alone will not resolve the root cause of the convergence issues. This demonstrates a failure to perform a proper root cause analysis and a tendency to apply superficial solutions. The professional decision-making process for similar situations should involve a systematic approach. 1. Understand the problem. Clearly define the observed issue, e.g., slow convergence instability and its impact. 2. Analyze the contributing factors. Investigate the network topology, protocol configurations, and traffic patterns. 3. Identify potential solutions. Brainstorm a range of technical options, considering their pros and cons. 4. Evaluate solutions against objectives. Assess how each solution aligns with performance goals, stability requirements, and resource constraints. 5. Implement and monitor. Deploy the chosen solution and continuously monitor its effectiveness, making adjustments as needed. 6. Document and learn. Record the process, outcomes, and lessons learned for future reference. Question 3. Compliance review shows that a critical financial application handling sensitive customer data is currently routed across the general corporate network without specific segmentation. A risk assessment has identified this as a significant vulnerability. Which of the following approaches best mitigates this risk by implementing effective network segmentation and access control for the application? Option A. Implement a dedicated VLAN for the application servers and clients, and configure a router ACL to permit only necessary traffic between this VLAN and other network segments. Option B. Configure the router to allow all traffic to and from the application servers to ensure unrestricted access and prevent any potential connectivity issues. Option C. Apply a broad ACL on the core router to filter traffic based on source and destination IP addresses for the application, without creating a separate VLAN. Option D. Rely solely on the application's built-in authentication and authorization features to protect the data, without implementing any network-level segmentation. Correct answer is A. Implement a dedicated VLAN for the application servers and clients, and configure a router ACL to permit only necessary traffic between this VLAN and other network segments. Explanation. Scenario analysis. This scenario presents a common challenge in network security and compliance, balancing the need for efficient network operations with the imperative to protect sensitive data from unauthorized access. The challenge lies in identifying the most effective and compliant method to segment traffic for a critical application, ensuring both performance and security, without violating the principles of network segmentation as understood within the context of Cisco routing and general IT security best practices. The risk assessment aspect is crucial because a misstep can lead to data breaches, service disruptions, or regulatory penalties. Correct approach analysis. Implementing a dedicated VLAN and a specific access control list (ACL) on the router is the best professional practice. This approach directly addresses the risk assessment by creating a logically isolated network segment (VLAN) for the sensitive application. The ACL then acts as a granular firewall, permitting only authorized traffic to and from this segment, thereby minimizing the attack surface. This aligns with the principle of least privilege and defense in depth, fundamental to secure network design and risk mitigation. It provides clear separation and controlled access, which are key objectives of network segmentation for risk reduction. Incorrect approaches analysis. Using a single, broad ACL to filter traffic for the application without VLAN segmentation is a less effective approach. While it attempts to control access, it doesn't provide the same level of isolation. If the application's traffic shares a subnet with other less sensitive traffic, a broad ACL might inadvertently block legitimate traffic or fail to prevent lateral movement by an attacker who compromises another device on the same subnet. This approach lacks the robust segmentation that a VLAN provides, increasing the overall risk profile. Simply relying on the application's internal security mechanisms without network-level segmentation is a significant regulatory and ethical failure. Network-level controls are a primary defense layer. Assuming application-level security is sufficient ignores the potential for network-based threats and vulnerabilities. This approach fails to implement a fundamental security control, leaving the sensitive data exposed to broader network risks and potentially violating data protection guidelines that mandate layered security. Broadly opening all ports for the application's traffic to simplify configuration is a direct contravention of risk assessment principles and security best practices. This approach maximizes the attack surface, exposing the application and its data to a wide range of potential threats. It demonstrates a disregard for security and compliance, creating a high-risk environment that is likely to fail any security audit and expose the organization to severe data breaches and associated penalties. Professional reasoning. Professionals should approach this by first understanding the sensitivity of the data and the criticality of the application. A thorough risk assessment would then identify potential threats and vulnerabilities. The chosen solution should directly mitigate these identified risks. In network design, segmentation is a primary tool for risk mitigation. Therefore, the decision-making process involves evaluating how well each proposed solution achieves effective segmentation and controlled access. The best practice is to implement controls that provide the highest level of isolation and granular access control, aligning with security frameworks and regulatory expectations for data protection. Question 4. Investigation of a proposed BGP configuration update on a critical Internet Edge router reveals potential changes to route filtering policies and as path manipulation. The network engineering team is under pressure to implement these changes quickly to address a perceived competitive advantage. What is the most professionally responsible approach to managing the risks associated with this configuration update? Option A. Focus solely on the technical aspects of the BGP configuration, ensuring it adheres to routing best practices, without extensive consideration for broader network or business impacts. Option B. Implement the BGP configuration changes immediately to gain the perceived competitive advantage, and address any issues that arise reactively. Option C. Perform a quick visual inspection of the configuration commands to ensure syntactical correctness. Then apply the changes. Option D. Conduct a thorough risk assessment, including impact analysis, vulnerability identification, and the development of a detailed rollback plan before proceeding with the implementation. The correct answer is D. Conduct a thorough risk assessment, including impact analysis, vulnerability identification, and the development of a detailed rollback plan before proceeding with the implementation. Explanation. Scenario analysis. This scenario presents a common challenge in network engineering where a critical routing protocol configuration change is proposed. The professional challenge lies in balancing the need for network stability and security against the imperative to implement necessary upgrades or fixes. The risk assessment approach is crucial because a misstep can lead to widespread network outages, data breaches, or service disruptions, all of which have significant financial and reputational consequences. The complexity arises from the interconnected nature of IP routing, where a seemingly minor change in one area can have cascading effects across the entire network. Therefore, a systematic and thorough risk assessment is paramount to identify potential vulnerabilities and mitigate them before implementation. Correct approach analysis. The correct approach involves a comprehensive risk assessment that includes a detailed analysis of the proposed BGP configuration changes, their potential impact on existing routing policies and security postures, and the development of robust rollback procedures. This aligns with best professional practices in network engineering, emphasizing proactive identification and mitigation of risks. Specifically, it adheres to the principles of network design and implementation that prioritize stability, security, and service availability. By thoroughly documenting potential risks, such as route leaks, denial of service vulnerabilities, or unintended policy violations, and planning mitigation strategies, the engineer demonstrates due diligence and a commitment to maintaining a secure and reliable network infrastructure. This approach is ethically sound as it prioritizes the integrity and availability of network services for all users and stakeholders. Incorrect approach is analysis. Implementing the changes immediately without a formal risk assessment is a significant regulatory and ethical failure. It demonstrates a disregard for established network management best practices and exposes the organization to unacceptable levels of risk. This approach could lead to severe service disruptions, potentially violating service-level agreements, SLAs, and incurring financial penalties. It also represents a failure in professional responsibility to ensure network stability and security. Performing a superficial review of the configuration without a structured risk assessment is also professionally unacceptable. While it might involve looking at the changes, it lacks the depth required to identify subtle but critical vulnerabilities. This approach fails to adequately consider the interconnectedness of routing protocols and the potential for unforeseen consequences, thus falling short of the due diligence expected of a network professional. Focusing solely on the technical implementation details without considering the broader security implications and potential impact on business operations is another failure. Network changes are not purely technical exercises. They have direct business consequences. Neglecting to assess these broader impacts, such as how routing changes might affect application performance or data access, is a critical oversight and a failure to act in the best interest of the organization. Professional reasoning. Professionals should approach network configuration changes with a structured risk assessment framework. This framework should include 1. Identification of potential risks. What could go wrong with this specific change? Consider technical failures, security vulnerabilities, and operational impacts. 2. Analysis of impact and likelihood. How severe would the consequences be if a risk materialized, and how likely is it to occur? 3. Development of mitigation strategies. What steps can be taken to reduce the likelihood or impact of identified risks? This includes testing, phased rollouts, and rollback plans. 4. Documentation and communication. Clearly document the risks, mitigation plan, and the rationale for the change. Communicate these to relevant stakeholders. 5. Monitoring and review. After implementation, continuously monitor the network for any adverse effects and review the effectiveness of the mitigation strategies. This systematic process ensures that changes are implemented responsibly, minimizing disruption and maintaining the integrity and security of the network. Question 5. What factors determine the most appropriate routing protocol selection for a new enterprise network deployment, considering both operational efficiency and inherent security considerations within the scope of Cisco IP routing best practices? Option A. The protocol's licensing costs and the vendor's market share in the routing industry. Option B. The protocol's support for authentication mechanisms and its susceptibility to common routing attacks. Option C. The protocol's widespread adoption and availability of third-party configuration guides. Option D. The protocol's ability to achieve the fastest convergence time under ideal network conditions. The correct answer is B. The protocol's support for authentication mechanisms and its susceptibility to common routing attacks. Explanation. This scenario presents a professional challenge in network design where the implementation of a routing protocol must balance performance requirements with the potential for security vulnerabilities. The challenge lies in selecting a protocol that meets the technical demands of the network while adhering to the implicit security considerations inherent in any network infrastructure, even if not explicitly codified as a regulation in the traditional sense for this exam scope. The CCNP Route V2.0 exam focuses on implementing Cisco IP routing, which inherently includes understanding the operational characteristics and security implications of various routing protocols. The correct approach represents best professional practice because it prioritizes a comprehensive risk assessment that considers the security posture of the chosen routing protocol. In the context of Cisco routing, this means evaluating protocols like OSPF or IGP not just for their convergence speed or scalability, but also for their susceptibility to attacks such as route injection, spoofing, or denial of service. A thorough assessment would involve understanding the authentication mechanisms available for these protocols, e.g., MD5 or SHA authentication for OSPF and IGP, and their effectiveness in the specific network environment. This proactive security consideration aligns with the principle of building secure and resilient networks, a fundamental aspect of professional network engineering. An incorrect approach that solely focuses on the fastest convergence time without considering security implications represents a significant regulatory and ethical failure. While the exam doesn't prescribe specific laws for routing protocol selection, there's an implicit professional standard and ethical obligation to design networks that are not unnecessarily vulnerable. Ignoring potential security weaknesses in a routing protocol can lead to network instability, data breaches, or service disruptions, all of which have severe professional consequences. For instance, selecting a protocol without authentication in a sensitive environment would be a direct contravention of best practices for network security, even if no explicit regulation mandates it for this specific protocol. Similarly, choosing a protocol based solely on ease of configuration without understanding its security implications would be professionally negligent. The professional decision-making process for similar situations should involve a structured risk assessment framework. This framework should begin with identifying potential threats and vulnerabilities associated with each routing protocol option. Next, it should involve evaluating the likelihood and impact of these threats. Finally, it should lead to the selection of a protocol and configuration that mitigates identified risks to an acceptable level, prioritizing security alongside performance and scalability. This iterative process ensures that technical decisions are informed by a holistic understanding of network integrity and operational resilience. Question 6. When evaluating the implementation of BGP for interdomain routing, which approach best mitigates the risk of unauthorized route advertisements and potential network disruption. Option A, relying solely on the default BGP configuration, assuming that standard protocol behavior prevents malicious route injections. Option B, prioritizing maximum route propagation to ensure all possible paths are advertised, without explicit filtering or authentication. Option C, disabling BGP security features to simplify configuration and reduce router overhead. Option D, implementing strong authentication mechanisms for BGP peering and employing route filtering to accept only legitimate prefixes. The correct answer is D, implementing strong authentication mechanisms for BGP peering and employing route filtering to accept only legitimate prefixes. Explanation: this scenario presents a professional challenge because network engineers are tasked with implementing routing protocols that directly impact the availability and security of sensitive data. The challenge lies in balancing the need for efficient routing with the imperative to protect against unauthorized access and potential disruption. A risk assessment approach is crucial here, as it requires a proactive identification and mitigation of potential vulnerabilities before they can be exploited. The correct approach involves a systematic evaluation of potential threats and vulnerabilities associated with the chosen routing protocol configuration. This includes analyzing how the protocol's features, such as authentication mechanisms, route filtering, and neighbor relationships, can be exploited. By understanding these risks, engineers can implement appropriate security controls and best practices, such as strong authentication for BGP neighbors, route summarization to limit the scope of routing information, and access control lists to restrict routing updates. This aligns with the general principles of network security and operational integrity expected in professional IT environments, ensuring that the network is not only functional but also resilient and secure. An incorrect approach would be to assume that the default configuration of a routing protocol is inherently secure, or that security concerns are secondary to routing efficiency. For instance, failing to implement authentication for BGP peering exposes the network to route injection attacks, where a malicious actor could advertise false routes, leading to traffic blackholing or redirection. Another failure would be to ignore the potential for misconfigurations that could lead to routing loops or excessive CPU utilization on routers, impacting network stability. These failures represent a disregard for due diligence and a lack of adherence to professional standards for network design and operation, potentially leading to significant business impact and reputational damage. Professionals should approach such situations by first understanding the specific routing protocol's security implications and then conducting a thorough risk assessment. This involves identifying assets, threats, vulnerabilities, and the potential impact of each. Based on this assessment, appropriate security controls and configuration best practices should be implemented and regularly reviewed. The decision-making process should prioritize security and stability alongside performance, ensuring a robust and reliable network infrastructure. Question 7. The performance metrics show a significant increase in packet loss and latency on a critical BGP peering session with a major internet service provider. Which of the following troubleshooting approaches is the most appropriate for a CCNP-level network engineer to take to diagnose and resolve this issue efficiently and effectively? Option A. Immediately reset the BGP peering session to re-establish a clean connection. Option B. Focus on analyzing BGP neighbor states, route advertisements, and local BGP configuration for anomalies. Option C. Begin troubleshooting general network congestion on unrelated internal network segments. Option D. Escalate the issue directly to the internet service provider, stating their network is likely the cause. The correct answer is A. Immediately reset the BGP peering session to re-establish a clean connection. Explanation: the performance metrics show a significant increase in packet loss and latency on a critical BGP peering session with a major internet service provider. This scenario is professionally challenging because it directly impacts the availability and performance of internet connectivity for a large customer base, potentially leading to financial losses and reputational damage. The network engineer must quickly diagnose the root cause while adhering to established operational procedures and Cisco's recommended best practices for BGP troubleshooting, as outlined in the CCNP Route V2.0 curriculum. The challenge lies in balancing the urgency of restoration with the need for a systematic and thorough investigation to prevent recurrence. The correct approach represents best professional practice because it involves a structured, evidence-based troubleshooting methodology. This aligns with the principles of network engineering and operational excellence, emphasizing proactive monitoring, systematic isolation of issues, and verification of configurations. By focusing on BGP-specific metrics and configurations, the engineer can efficiently pinpoint the problem without unnecessary disruption. This methodical approach minimizes the risk of introducing new issues and ensures a stable resolution, reflecting a commitment to service reliability. An incorrect approach that involves immediately resetting the BGP peering without gathering sufficient diagnostic data is professionally unacceptable. This action bypasses the critical step of understanding the underlying cause, which could be a configuration error, a hardware issue, or a problem on the ISP's network. Such a hasty action could mask the true problem, leading to its recurrence, and could also violate service level agreements, SLAs, if it causes an extended outage or if the reset itself is not permitted without prior notification or investigation. It demonstrates a lack of due diligence and a failure to apply systematic troubleshooting principles. Another incorrect approach, such as solely blaming the ISP without performing local diagnostics, is also professionally unsound. While the ISP's network is a potential point of failure, a responsible network engineer must first exhaust all possibilities within their own network. Failing to do so represents a premature conclusion and a potential misallocation of resources. It can lead to unnecessary escalations with the ISP and delays in resolving an issue that might be internally caused. This approach neglects the fundamental responsibility of network ownership and troubleshooting. A third incorrect approach, focusing on unrelated network segments or protocols, demonstrates a lack of understanding of the specific problem domain. BGP issues are distinct from general network congestion or routing problems on internal links. Diverting attention to irrelevant areas wastes valuable time and resources, prolonging the outage and increasing the risk of customer dissatisfaction. It signifies a failure to apply the correct troubleshooting framework and a lack of expertise in BGP troubleshooting as expected at the CCNP level. The professional decision-making process for similar situations should involve 1. Acknowledging the urgency and impact of the issue. 2. Activating the incident response plan. 3. Gathering all available performance data and logs related to the affected BGP session. 4. Systematically analyzing BGP state, neighbor status, route advertisements, and network reachability. 5. Isolating the problem by examining local configurations, hardware, and connectivity before engaging external parties. 6. Documenting all steps taken and findings. 7. Implementing a permanent fix and verifying its effectiveness. Question 8. Quality control measures reveal that a critical BGP peering session with a key business partner is experiencing intermittent packet loss, impacting transaction processing. A senior network engineer believes they know the cause and can fix it with a minor adjustment to the BGP neighbor configuration. What is the most appropriate course of action to address this situation? Option A. Temporarily disable the BGP peering session to fully isolate the issue and prevent further packet loss, then troubleshoot the configuration offline. Option B. Document the proposed change, assess its potential impact, develop a rollback plan, and submit a change request for approval through the established change management process before implementation. Option C. Proceed with the configuration change during the next scheduled maintenance window, assuming that any issues will be resolved before the window closes. Option D. Immediately implement the proposed configuration change on the BGP neighbor, as the engineer has a high degree of confidence in the solution, and the issue is impacting business operations. The correct answer is D. Immediately implement the proposed configuration change on the BGP neighbor, as the engineer has a high degree of confidence in the solution, and the issue is impacting business operations. Explanation. The scenario presents a common challenge in network operations, ensuring the integrity and security of routing information in a production environment. The professional challenge lies in balancing the need for rapid troubleshooting and configuration changes with the imperative to maintain network stability and prevent unauthorized access or malicious manipulation of routing protocols. The specific context of the CCNP route exam implies a focus on Cisco IOS-based routing, and the implied jurisdiction is a general business/enterprise environment where adherence to best practices and security policies is paramount. The correct approach represents best professional practice because it prioritizes a structured, documented, and authorized process for any changes to critical routing configurations. This aligns with industry standards for network change management, which are designed to minimize risk and ensure accountability. By involving a change advisory board, CAB, or a designated approval authority, the organization ensures that potential impacts are assessed by multiple stakeholders, including security, operations, and potentially business units. The requirement for a rollback plan is crucial for mitigating unforeseen issues, demonstrating due diligence, and adhering to principles of operational resilience. This systematic approach prevents ad hoc modifications that could lead to outages, security breaches, or performance degradation, all of which have significant business implications. An incorrect approach that involves immediate, unapproved configuration changes by a senior engineer, even with good intentions, represents a significant regulatory and ethical failure. This bypasses established change control procedures, which are often mandated by internal policies and potentially by industry compliance frameworks, though specific regulations are not cited for this exam. The principle of adherence to policy is universal in professional IT. Such actions undermine accountability, making it difficult to trace the root cause of future problems and potentially exposing the network to vulnerabilities if the changes are not thoroughly vetted. It also sets a dangerous precedent, encouraging a culture of bypassing established protocols. Another incorrect approach, such as implementing changes during a scheduled maintenance window without prior approval or a documented plan, is also professionally unacceptable. While maintenance windows are intended for changes, they do not negate the need for proper authorization and planning. This approach still lacks the necessary risk assessment and stakeholder buy-in, increasing the likelihood of unintended consequences. The absence of a rollback plan is a critical oversight, leaving the network vulnerable to extended downtime if issues arise. Finally, an approach that involves disabling routing protocols to isolate a perceived issue without a clear understanding of the impact or a plan to re-enable them is highly risky. This is a drastic measure that can lead to widespread network disruption and is not a substitute for proper troubleshooting and configuration management. It demonstrates a lack of methodical problem solving and a failure to adhere to established operational procedures designed to maintain service continuity. The professional decision-making process for similar situations should involve a clear understanding of the organization's change management policy. When a network issue arises, the first step is to gather information and assess the impact. If a configuration change is deemed necessary, the engineer must follow the established change control process, which typically includes documenting the proposed change, assessing the risks, developing a rollback plan, and obtaining the necessary approvals from relevant stakeholders or a CAB. This structured approach ensures that changes are made in a controlled and predictable manner, minimizing the risk of negative impacts on the network and the business. Question 9. Stakeholder feedback indicates a strong preference for implementing IGAP across a new multi-site enterprise network due to its perceived ease of configuration and rapid convergence. However, the network is expected to grow significantly in terms of sites and user base over the next 5 years, and traffic patterns are becoming increasingly complex with the adoption of cloud-based services. Considering the principles of robust IP routing and network scalability, which of the following approaches best addresses the long-term implications of this routing protocol decision? Option A. Deploy IGAP with a focus on basic configuration, assuming that any future scalability or performance issues can be addressed with incremental adjustments and troubleshooting as they arise. Option B. Prioritize IGAP due to its familiarity within the organization, even if a detailed analysis suggests that other routing protocols might offer better long-term scalability and efficiency for the projected network growth. Option C. Implement IGAP immediately across the network as requested by stakeholders, leveraging existing team expertise to expedite deployment and address immediate connectivity needs. Option D. Conduct a comprehensive evaluation of IGAP suitability for the current and projected network scale, traffic patterns, and convergence requirements, comparing its advantages and disadvantages against alternative routing protocols to ensure optimal long-term performance and stability. Correct answer is D. Conduct a comprehensive evaluation of IGAP suitability for the current and projected network scale, traffic patterns, and convergence requirements, comparing its advantages and disadvantages against alternative routing protocols to ensure optimal long-term performance and stability. Explanation. Scenario analysis. This scenario presents a common challenge in network design where a critical routing protocol, IGAP, is being considered for deployment across a multi-site enterprise network. The challenge lies in balancing the protocol's ease of configuration and rapid convergence with the potential for suboptimal routing decisions and scalability issues in larger, more complex environments. Stakeholder feedback, often driven by immediate operational needs or past experiences, can sometimes overlook long-term implications. The professional challenge is to evaluate IGAP suitability against established best practices and potential future growth, ensuring that the chosen routing solution aligns with both current requirements and strategic objectives, while adhering to the principles of efficient and reliable IP routing as outlined in the CCNP route curriculum. Correct approach analysis. The correct approach involves a thorough evaluation of IGAP suitability for the specific network topology and scale, considering its advantages and disadvantages. This includes assessing its ability to handle the expected traffic volumes, its convergence speed in relation to application requirements, and its potential for administrative overhead as the network grows. Best professional practice dictates a proactive assessment of IGAP limitations, such as its reliance on a single metric for path selection, and its potential for suboptimal routing in complex topologies with multiple equal-cost paths. This approach emphasizes a deep understanding of routing protocol behavior and its impact on network performance and stability, aligning with the core competencies tested in the CCNP route exam, which focuses on implementing and troubleshooting IP routing. The decision should be informed by a comprehensive understanding of IGAP characteristics and how they map to the organization's technical and business requirements. Prioritizing long-term network health and efficiency. Incorrect approaches analysis. Implementing IGAP without a detailed analysis of its suitability for the specific network topology and scale is a significant regulatory and ethical failure. This approach ignores the fundamental principles of sound network design and routing protocol selection, which are implicitly governed by the need for reliable and efficient data transmission. Such a decision could lead to suboptimal routing, increased convergence times during network events, and potential scalability issues, all of which violate the implicit expectation of providing a robust and performant network infrastructure. This is an ethical failure as it prioritizes expediency over due diligence, potentially leading to future operational problems and increased costs for remediation. Adopting IGAP solely because it is familiar or has been used in previous, smaller deployments, without considering the current network's specific characteristics and future growth projections, represents a failure to apply best practices. This approach risks perpetuating potentially inadequate solutions and can lead to network instability or performance degradation. Ethically, it demonstrates a lack of commitment to continuous learning and adaptation, which are crucial in the rapidly evolving field of network engineering. It also fails to meet the implicit regulatory requirement of providing a network that is fit for purpose and capable of supporting business operations effectively. Choosing IGAP based on a superficial understanding of its features, without delving into its metric calculation, convergence behavior, or its suitability for the intended network size and complexity, is a critical professional oversight. This can lead to misconfigurations and unexpected routing loops or black holes, directly impacting network reliability. Such an approach is professionally unsound and ethically questionable, as it risks deploying a solution that is not adequately understood, potentially jeopardizing network integrity and the services it supports. Professional reasoning. Professionals should approach routing protocol selection by first understanding the network's requirements, including topology, scale, traffic patterns, and convergence needs. This should be followed by a comparative analysis of available routing protocols, evaluating their strengths and weaknesses against these requirements. A deep dive into the technical specifics of each protocol, including their metrics, administrative distance, convergence mechanisms, and scalability, is essential. The decision-making process should prioritize long-term stability, efficiency, and manageability, rather than solely relying on familiarity or ease of initial configuration. Documentation of the evaluation process and the rationale behind the chosen protocol is also a critical component of professional practice. Question 10. Strategic planning requires that network administrators carefully consider the implications of routing protocol configurations on overall network security and compliance. When designing an IP routing infrastructure, which approach best ensures that routing decisions do not inadvertently expose sensitive network segments or violate established access control policies, thereby maintaining regulatory adherence. Option A. Assuming that the inherent security features of routing protocols are sufficient to protect the network from unauthorized route propagation. Option B. Disabling all routing updates and manually configuring static routes for every network segment to prevent dynamic route exchange. Option C. Implementing route filtering and access control lists directly within the routing protocol configurations to control route advertisement and acceptance. Option D. Relying solely on firewall policies at the network perimeter to prevent unauthorized access to internal routing tables. The correct answer is C. Implementing route filtering and access control lists directly within the routing protocol configurations to control route advertisement and acceptance. Explanation. The scenario presents a common challenge in network design and implementation, balancing performance requirements with the need for robust security and compliance. In the context of Cisco IP routing, specifically within the scope of the 300-101 Route of 2.0 exam, understanding how routing protocols interact with security policies is paramount. The challenge lies in ensuring that routing decisions do not inadvertently create security vulnerabilities or violate established network access policies, which are often dictated by organizational compliance mandates. The correct approach emphasizes a proactive and integrated strategy, where security is considered from the outset of routing protocol design. This aligns with best practices in network engineering, where security is not an afterthought but a fundamental component of the architecture. By implementing access control lists, ACL, and route filtering mechanisms directly within the routing configuration, administrators can enforce granular control over which routes are advertised and accepted. This directly addresses potential security risks such as route injection attacks or the unauthorized propagation of sensitive network information. This approach is professionally sound because it embeds security controls at the network layer, making them an intrinsic part of the routing process, and thus more effective and less prone to bypass. Incorrect approaches often stem from a lack of integration between routing and security functions. For instance, relying solely on perimeter security devices without addressing internal routing policies can leave internal segments vulnerable. Similarly, assuming that routing protocols inherently provide security is a dangerous misconception. Each incorrect approach fails to adequately address the specific regulatory or ethical considerations that govern network operations. These might include data privacy regulations, industry-specific compliance standards, e.g., PCI DSS for financial data, HIPAA for healthcare, or internal corporate security policies. The failure to implement appropriate routing security measures can lead to data breaches, unauthorized access, and significant legal and financial repercussions. The professional decision-making process for such situations involves a thorough understanding of the network's purpose, the data it carries, and the applicable regulatory landscape. It requires a risk-based assessment, identifying potential threats to routing information and implementing controls that mitigate those risks. This involves consulting security policies, compliance requirements, and network architecture documentation. A systematic approach, starting with a clear definition of security objectives and then designing routing configurations to meet those objectives, is crucial. Regular review and auditing of routing configurations against security and compliance standards are also essential to maintain a secure and compliant network posture. Question 11. Benchmark analysis indicates that a network engineering team is proposing the implementation of a new dynamic routing protocol to enhance network scalability and convergence times within a large enterprise environment. Considering the critical nature of the existing infrastructure and the potential impact of routing changes, which of the following approaches best aligns with professional best practices for implementing such a significant network modification? Option A. Implement the new routing protocol in a basic lab environment that only includes a few routers, and then proceed with a full production deployment. Option B. Prioritize the configuration of the new routing protocol's advanced features, and then address security integration and testing after the initial deployment. Option C. Immediately deploy the new routing protocol across the entire production network to realize its benefits as quickly as possible. Option D. Conduct a comprehensive design and simulation phase, followed by a pilot deployment in a staging environment that mirrors production, and then a phased rollout with robust monitoring and rollback capabilities. The correct answer is D. Conduct a comprehensive design and simulation phase, followed by a pilot deployment in a staging environment that mirrors production, and then a phased rollout with robust monitoring and rollback capabilities. Explanation. Scenario analysis. This scenario presents a common challenge in network design, where the implementation of a new routing protocol needs to be carefully evaluated against existing operational requirements and potential impacts. The professional challenge lies in balancing the benefits of a new protocol, e.g., scalability, convergence speed, with the risks of disruption, security vulnerabilities, and compliance with established network policies. A hasty or ill-considered implementation can lead to significant downtime, security breaches, and non-compliance, all of which have direct financial and reputational consequences. The need for a thorough, phased approach is paramount. Correct approach analysis. The correct approach involves a comprehensive, multi-stage evaluation process that prioritizes stability and security. This begins with a detailed design and simulation phase, followed by a controlled pilot deployment in a non-production environment. Subsequently, a phased rollout with robust monitoring and rollback capabilities is essential. This methodology aligns with best practices in network engineering and IT governance, which emphasize risk mitigation, change control, and validation before full production deployment. From a regulatory and ethical standpoint, this approach demonstrates due diligence, ensuring that the network remains available, secure, and compliant with internal policies and any relevant industry standards that might govern network operations and data integrity. The focus on testing and validation minimizes the risk of unintended consequences that could lead to service disruption or security compromises. Incorrect approaches analysis. Implementing a new routing protocol directly into the production environment without prior testing or simulation is a significant regulatory and ethical failure. It demonstrates a disregard for operational stability and security, potentially violating service-level agreements, SLAs, and internal IT policies that mandate change control and risk assessment. This approach exposes the organization to a high probability of network outages, data corruption, or security vulnerabilities, which could have severe financial and legal repercussions. Deploying the new routing protocol only in a lab environment that does not accurately reflect the production network's complexity and traffic patterns is also professionally unacceptable. While some testing is better than none, a lab simulation that lacks fidelity can lead to a false sense of security. If the protocol behaves differently under real-world conditions, the subsequent production deployment could still result in unexpected issues, violating the principle of thorough validation, and potentially leading to non-compliance with operational standards. Focusing solely on the theoretical performance benefits of the new routing protocol, without considering its integration with existing security infrastructure and access control lists, ACL, represents a critical oversight. Routing protocols can inadvertently create new security paths or bypass existing security controls. Failing to integrate security considerations from the outset is a direct violation of security best practices and could lead to compliance breaches if sensitive data is exposed. Professional reasoning. Professionals should adopt a structured approach to network changes, guided by established ITIL or similar frameworks. This involves a clear understanding of the business requirements, a thorough risk assessment, detailed design and planning, rigorous testing in representative environments, a controlled deployment strategy with rollback plans, and continuous monitoring post-implementation. The decision-making process should always prioritize network stability, security, and compliance, ensuring that any changes are beneficial and do not introduce unacceptable risks. Question 12. Quality control measures reveal that a network upgrade involves the implementation of IGAP across a multi-vendor infrastructure. To ensure optimal routing performance and prevent potential network instability, what is the most professional and risk-averse approach to deploying IGAP in this environment? Option A. Deploy IGAP with default configurations across all routers and address any interoperability issues as they arise during normal network operation. Option B. Deploy IGAP on a limited number of routers, simulate production traffic, and meticulously verify routing table convergence, metric calculations, and path selection before expanding the deployment. Option C. Implement IGAP on a small subset of routers, focusing only on verifying basic IP connectivity between these initial routers. Option D. Enable IGAP on all routers simultaneously, relying on post-deployment monitoring tools to detect and address any routing anomalies. The correct answer is B. Deploy IGAP on a limited number of routers, simulate production traffic, and meticulously verify routing table convergence, metric calculations, and path selection before expanding the deployment. Explanation. Scenario analysis. This scenario presents a common challenge in network design and implementation where a critical routing protocol, IGAP, is being deployed in a multi-vendor environment. The challenge lies in ensuring interoperability and preventing suboptimal routing decisions that could impact network performance and stability. The use of IGAP in a mixed environment necessitates careful consideration of its proprietary nature and the potential for configuration drift or misinterpretation across different vendor platforms. The need for a robust validation process before full deployment is paramount to avoid widespread network disruption. Correct approach analysis. The correct approach involves a phased, controlled deployment with rigorous testing and validation at each stage. This aligns with best practices in network engineering, emphasizing a crawl, walk, run methodology. Specifically, deploying IGAP on a limited set of routers, simulating production traffic, and meticulously verifying routing table convergence, metric calculations, and path selection ensures that the protocol behaves as expected across different vendor implementations. This proactive validation minimizes the risk of introducing routing loops, black holes, or inefficient traffic flows once the protocol is enabled across the entire network. This approach directly addresses the potential for interoperability issues inherent in a multi-vendor IGAP deployment, safeguarding network integrity and performance. Incorrect approach is analysis. Enabling IGAP on all routers simultaneously without prior testing in a mixed vendor environment is a significant regulatory and ethical failure. It demonstrates a disregard for network stability and a lack of due diligence. This approach risks widespread routing instability, service outages, and potential data loss, which could have severe business and reputational consequences. It violates the implicit professional obligation to implement changes in a manner that minimizes risk to the operational network. Implementing IGAP with default settings across all routers and relying solely on post-deployment monitoring to identify issues is also professionally unacceptable. Monitoring is crucial. It is a reactive measure. The failure here is the absence of proactive validation. This approach assumes that default configurations will be universally compatible and effective, which is often not the case in multi-vendor scenarios, especially with proprietary protocols like IGAP. This can lead to unexpected behavior and prolonged troubleshooting periods, impacting network availability and user experience. Deploying IGAP on a small subset of routers, but only testing basic connectivity without verifying routing table accuracy and metric consistency is insufficient. This approach fails to address the core complexities of IGAP in a multi-vendor environment. Routing table accuracy and consistent metric calculation are critical for optimal path selection. Neglecting these aspects during testing can lead to subtle but significant routing inefficiencies, or even routing loops that might not be immediately apparent during basic connectivity tests. Professional reasoning. Professionals must adopt a risk-averse and methodical approach to network changes, especially those involving core routing protocols in heterogeneous environments. The decision-making process should prioritize thorough planning, staged implementation, and comprehensive validation. This involves understanding the specific characteristics and potential interoperability challenges of the chosen routing protocol across different vendor platforms. A robust testing strategy, including simulation and pilot deployments, is essential to identify and remediate issues before they impact the production network. Professionals have an ethical responsibility to ensure the stability and reliability of the networks they manage, and this requires a proactive, evidence-based approach to change management. Question 13. Operational review demonstrates that a specific area within an OSPF-enabled network is experiencing intermittent routing instability and high CPU utilization on several routers. Analysis of OSPF database summaries indicates a disproportionately high number of Type 5 LSAs being generated and flooded within this area, impacting convergence times and overall network performance. Which of the following approaches best addresses this operational challenge while adhering to best practices for OSPF implementation? Option A. Implement route summarization at the area border router Aber, connecting the affected area to the backbone area, and investigate the source of the excessive Type 5 LSAs to determine if they can be aggregated or filtered closer to their origin. Option B. Manually adjust the LSA retransmission timers for Type 5 LSAs across all routers in the network to reduce their frequency. Option C. Increase the CPU and memory resources of the routers experiencing high utilization to accommodate the increased LSA flooding. Option D. Disable OSPF on the routers within the affected area to prevent further LSA flooding. The correct answer is A. Implement route summarization at the area border router Aber, connecting the affected area to the backbone area, and investigate the source of the excessive Type 5 LSAs to determine if they can be aggregated or filtered closer to their origin. Explanation. This scenario presents a common challenge in network operations, balancing the immediate need for network stability with the long-term implications of configuration choices. The professional challenge lies in understanding the subtle but significant differences between routing protocol behaviors and their impact on network convergence, security, and resource utilization, all within the context of maintaining a compliant and efficient routing infrastructure. The correct approach, which involves a thorough understanding of OSPF LSA types and their propagation, represents best professional practice because it directly addresses the root cause of potential instability. By identifying and mitigating the specific LSA type that is causing excessive flooding, the network engineer is implementing a targeted and effective solution. This proactive measure prevents unnecessary CPU and memory load on routers, reduces the likelihood of routing loops or black holes, and ensures that the routing table accurately reflects the network topology. This aligns with the general principles of network design and operation that emphasize stability, efficiency, and predictability, which are implicitly expected in any professional IT environment governed by Cisco's routing best practices. An incorrect approach that focuses solely on increasing router hardware resources without addressing the underlying LSA flooding issue is professionally unacceptable. This is akin to treating a symptom rather than the disease. While it might temporarily alleviate the problem, it does not resolve the inefficient use of network resources and could mask a more fundamental design flaw. Ethically, it represents a failure to apply due diligence in troubleshooting and problem resolution, potentially leading to recurring issues and increased operational costs. Another incorrect approach that involves disabling OSPF altogether on the affected segment without a clear understanding of the impact on network reachability is also professionally unsound. This action would likely lead to widespread connectivity issues, impacting business operations and potentially violating service-level agreements. It demonstrates a lack of understanding of OSPF's role in the network and a failure to implement a controlled and phased approach to network changes. The ethical implication here is a disregard for network stability and user impact. Finally, an approach that involves manually manipulating LSA timers without a deep understanding of their interdependencies and the potential for unintended consequences is highly risky. While OSPF timers can be tuned, doing so without a comprehensive analysis of the network's specific requirements and the behavior of different LSA types can lead to routing instability, increased convergence times, or even routing loops. This demonstrates a lack of expertise and a failure to follow established best practices for OSPF tuning, which typically involves careful planning and testing. The professional reasoning process for this situation should involve a systematic approach. First, accurately identify the symptoms of network instability. Second, leverage network monitoring tools and protocol analysis to pinpoint the specific cause, in this case, excessive LSA flooding. Third, understand the different OSPF LSA types and their propagation characteristics. Fourth, evaluate potential solutions based on their effectiveness, efficiency, and potential side effects. Finally, implement the chosen solution in a controlled manner, with thorough testing and verification to ensure network stability and performance are restored and maintained. Question 14. The evaluation methodology shows that a network administrator is tasked with optimizing BGP convergence time in a large enterprise network. They are considering adjusting the BGP keep-live and hold-down timers. Which of the following approaches best aligns with the principles of robust and stable IP routing as expected in a professional implementation scenario? Option A. Rely solely on the default BGP timer values provided by the vendor, as these are pre-configured for optimal performance in most scenarios. Option B. Incrementally adjust BGP timers based on observed network behavior and stability, thoroughly testing each change in a controlled environment before production deployment. Option C. Drastically reduce BGP keep-live and hold-down timers across all BGP peers to achieve the fastest possible convergence, assuming faster is always better. Option D. Increase BGP hold-down timers significantly to prevent any potential routing flaps, even if it means a substantial delay in detecting actual link failures. The correct answer is B. Incrementally adjust BGP timers based on observed network behavior and stability, thoroughly testing each change in a controlled environment before production deployment. Explanation: this scenario presents a common challenge in network design and implementation, where a critical routing protocol configuration needs to be validated against established best practices and the specific requirements of the 300-101 CCNP implementing Cisco IP routing, Route v2. 0. Exam syllabus. The professional challenge lies in ensuring that the chosen configuration not only functions correctly, but also adheres to principles of scalability, stability, and security, which are paramount in enterprise routing environments. Misconfigurations can lead to network instability, security vulnerabilities, and performance degradation, all of which have significant operational and financial implications. The correct approach emphasizes a holistic evaluation that considers the impact of routing protocol timers on network convergence and stability. Specifically, tuning BGP timers, like keep-live and hold-down timers, requires a deep understanding of the protocol's behavior under various network conditions. Adjusting these timers too aggressively can lead to premature neighbor adjacency loss and routing instability, while setting them too conservatively can delay the detection of actual link failures, impacting convergence time. Best professional practice dictates a measured approach, often involving incremental adjustments and thorough testing in a lab environment before deployment in production. This aligns with the exam's focus on implementing robust and resilient routing solutions. An incorrect approach might involve blindly applying default timer values without understanding their implications. While defaults are often conservative, they may not be optimal for all network topologies or traffic patterns. Another incorrect approach could be to drastically reduce timers to achieve faster convergence, without considering the increased risk of false adjacency flaps due to transient network issues or processing delays. This would be a regulatory failure in the context of the exam's implied standards for stable and reliable routing. Furthermore, making changes without proper documentation and rollback plans is a significant ethical and professional failing, as it hinders troubleshooting and recovery efforts. Professional decision-making process should involve a thorough understanding of the routing protocol's mechanics, the specific network requirements, and the potential trade-offs associated with any configuration change. This includes performing impact analysis, conducting lab testing, implementing changes during maintenance windows, and having robust monitoring and rollback procedures in place. The goal is to achieve a balance between rapid convergence and network stability, ensuring the overall health and performance of the IP routing infrastructure. Question 15. Risk assessment procedures indicate a potential vulnerability in the network's core routing infrastructure, where unauthorized routers could inject falsified routing information, leading to traffic redirection and potential denial of service conditions. Which of the following implementation strategies best mitigates this specific risk by ensuring the authenticity and integrity of routing advertisements? Option A. Disabling all routing protocol authentication mechanisms to simplify configuration and reduce overhead. Option B. Relying solely on static route configurations for critical network paths. Option C. Implementing route map policies to filter all incoming and outgoing routing updates based on prefix lists. Option D. Configuring message digest algorithm authentication between all adjacent routing protocol neighbors. Correct answer is C. Implementing route map policies to filter all incoming and outgoing routing updates based on prefix lists. Explanation: scenario analysis. This scenario presents a common implementation challenge in enterprise routing environments, ensuring consistent and secure routing policy enforcement across a distributed network. The challenge lies in the potential for misconfigurations to propagate, leading to security vulnerabilities or service disruptions. The need for a robust and auditable method to verify the integrity of routing advertisements is paramount, especially when dealing with sensitive internal data or critical business applications. The professional challenge is to select a method that is both technically sound and aligns with best practices for network security and operational integrity, without introducing undue complexity or performance overhead. Correct approach analysis. The correct approach involves leveraging a protocol feature that cryptographically verifies the origin and integrity of routing updates. This directly addresses the risk of unauthorized or tampered routing information. By implementing a mechanism that requires authentication of routing advertisements, the network administrator can ensure that only legitimate routers are participating in the routing process and that the advertised routes have not been altered in transit. This aligns with the principle of least privilege and defense in depth in network security. It provides a verifiable audit trail and significantly reduces the attack surface related to routing manipulation. Incorrect approaches analysis. One incorrect approach would be to rely solely on access control lists, ACL, to filter routing updates. While ACLs can restrict which prefixes are advertised or accepted, they do not provide any inherent mechanism to verify the authenticity or integrity of the source of the routing information. A malicious actor could still inject false routes if they are within the permitted prefix ranges. This fails to address the core risk of route injection or modification from an untrusted source. Another incorrect approach would be to disable all routing protocol authentication. This completely removes any layer of security for routing advertisements, making the network highly susceptible to various routing attacks, including route hijacking and denial of service attacks. It represents a significant ethical and professional failure to protect the network infrastructure and the data it carries. A third incorrect approach would be to implement route maps without any underlying authentication. Route maps are powerful for policy manipulation, but on their own, do not authenticate the origin of the routes being processed. They can filter or modify routes, but they cannot prevent a compromised router from advertising incorrect or malicious routes in the first place. This approach is insufficient for verifying the trustworthiness of routing information. Professional reasoning. Professionals must adopt a proactive and security-conscious approach to network design and implementation. When faced with routing security challenges, the decision-making process should prioritize mechanisms that provide verifiable assurance of authenticity and integrity. This involves understanding the capabilities of routing protocols and their associated security features. A systematic approach would involve 1. Identifying potential threats to routing stability and security. 2. Evaluating available protocol features and technologies that mitigate these threats. 3. Selecting the most effective and efficient solution that balances security, performance, and manageability. 4. Implementing the chosen solution with rigorous testing and verification. 5. Establishing ongoing monitoring and auditing procedures to ensure continued security and compliance. Question 16. Governance review demonstrates that a new network segment is being planned, and the engineering team is considering implementing IGAP for routing. However, the review also highlights the need to ensure that any routing protocol implementation aligns with the organization's established routing policies and does not introduce conflicts with existing routing protocols in other parts of the network. What is the most appropriate approach to selecting and implementing IGAP in this scenario? Option A. Conduct a thorough evaluation of IGAP suitability against the organization's established routing policies and its compatibility with existing routing protocols, ensuring it meets security and operational requirements. Option B. Select IGAP based solely on its advanced features, without a comprehensive assessment of its impact on the overall routing domain and its adherence to established network standards. Option C. Deploy IGAP without a detailed review of existing routing policies or potential conflicts, prioritizing rapid deployment to meet project timelines. Option D. Implement IGAP immediately due to its perceived ease of configuration and its Cisco proprietary nature, assuming seamless integration with other Cisco devices. The correct answer is A. Conduct a thorough evaluation of IGAP suitability against the organization's established routing policies and its compatibility with existing routing protocols, ensuring it meets security and operational requirements. Explanation. Scenario analysis. This scenario presents a common challenge in network design and implementation, where a critical routing protocol, IGP, is being considered for a new segment of the network. The professional challenge lies in ensuring that the chosen routing protocol aligns with the organization's existing infrastructure, security policies, and operational capabilities, while also considering future scalability and interoperability. The need to adhere to established routing policies and avoid potential conflicts with other routing protocols is paramount. The decision-making process requires a thorough understanding of IGP characteristics and its implications within the broader network context, rather than a superficial selection based on perceived ease of implementation. Correct approach analysis. The correct approach involves a comprehensive evaluation of IGP suitability against the organization's established routing policies and its compatibility with existing routing protocols. This includes assessing IGP convergence characteristics, its administrative distance, its metric calculation, and its potential for creating routing loops or instability when interacting with other protocols. Best professional practice dictates that any new routing protocol implementation must be validated against documented network standards and security guidelines. This ensures that the network remains stable, secure, and manageable, and that all routing decisions are justifiable and auditable. Adhering to these policies prevents unauthorized or suboptimal configurations that could lead to network outages or security breaches. Incorrect approaches analysis. Implementing IGP without a thorough review of existing routing policies and potential conflicts is a significant regulatory and ethical failure. It bypasses established governance procedures designed to maintain network integrity and security. This approach risks introducing routing instability, security vulnerabilities, and operational complexities that could have been foreseen and mitigated. It demonstrates a lack of due diligence and a disregard for the organization's established network architecture and security posture. Selecting IGP solely based on its perceived ease of configuration, without considering its impact on the overall routing domain, is also professionally unacceptable. This decision prioritizes expediency over robust network design and operational stability. It fails to account for potential issues such as metric manipulation, unequal cost load balancing complexities, or the administrative overhead of managing IGP unique features in a mixed protocol environment. This can lead to suboptimal routing paths, increased troubleshooting time, and potential network performance degradation. Choosing IGP because it is a Cisco proprietary protocol, assuming it will seamlessly integrate with other Cisco devices, is a flawed assumption. While it offers advantages within a Cisco-only environment, its implementation still requires careful consideration of its interaction with other routing protocols and its adherence to overall network design principles. Relying solely on vendor affiliation without a technical and policy-based evaluation is a failure to apply sound engineering judgment and can lead to unexpected interoperability issues or security gaps. Professional reasoning. Professionals should approach routing protocol selection by first understanding the business and technical requirements of the network segment. This involves consulting existing network design documents, routing policies, and security standards. A comparative analysis of candidate routing protocols should then be performed, focusing on their convergence speed, scalability, security features, interoperability, and operational complexity. The decision should be documented, including a justification for the chosen protocol and a plan for its implementation and testing. Regular reviews and audits of routing configurations are essential to ensure ongoing compliance and network health. Question 17. Benchmark analysis indicates that a multinational corporation's edge routers are currently advertising all learned internal routes to their external BGP peers. This practice poses a significant security risk by exposing internal network topology and potentially allowing the acceptance of malicious routing information from external sources. The network administrator needs to implement a robust solution to control the routes advertised to and accepted from external peers, ensuring that only authorized and validated routing information is exchanged without compromising network connectivity. Option A. Advertise all learned internal routes to external BGP peers without any modifications. Option B. Disable all BGP updates to external peers. Option C. Configure access control lists, ACL, on the edge routers to permit or deny traffic based on source and destination IP addresses. Option D. Implement route filtering using prefix lists and route maps on the edge routers to control advertised and accepted routes. The correct answer is D. Implement route filtering using prefix lists and route maps on the edge routers to control advertised and accepted routes. Explanation. Scenario analysis. This scenario presents a common implementation challenge in enterprise networks, ensuring consistent and secure routing policies across a distributed infrastructure while adhering to evolving security best practices. The challenge lies in balancing the need for efficient data flow with the imperative to prevent unauthorized access and data exfiltration, especially when dealing with sensitive internal resources. The complexity arises from the potential for misconfigurations to create security vulnerabilities or routing loops, impacting network availability and performance. Professionals must exercise careful judgment to select and implement the most appropriate security measures without disrupting legitimate network operations. Correct approach analysis. The correct approach involves implementing route filtering using prefix lists and route maps on the edge routers. This method allows for granular control over which routes are advertised to and accepted from external networks. By defining specific prefixes that are permitted or denied, administrators can enforce a policy that prevents the advertisement of internal network information to untrusted external entities, and also prevents the acceptance of potentially malicious or incorrect routes from the outside. This aligns with the principle of least privilege in routing, ensuring that only necessary and validated routing information is exchanged. This proactive filtering minimizes the attack surface and enhances network stability by preventing the propagation of invalid routing updates. Incorrect approaches analysis. Advertising all learned routes to external peers without any filtering is a significant security and operational failure. This exposes internal network topology and IP addressing schemes to potentially untrusted parties, which can be exploited for reconnaissance and targeted attacks. It also increases the risk of accepting invalid or suboptimal routes from external peers, leading to routing instability and blackholing of traffic. Implementing a simple access control list, ACL, to permit or deny traffic based on source or destination IP addresses, while useful for traffic filtering, is not directly applicable to controlling route advertisements themselves. ACLs operate at the packet forwarding layer, whereas route filtering operates at the routing protocol information exchange layer. Therefore, an ACL would not prevent the advertisement or acceptance of specific routes by the routing protocol. Disabling all BGP updates to external peers would effectively isolate the internal network from the external world, which is usually not a desired outcome for an enterprise network that requires connectivity. While it might seem like a security measure, it negates the purpose of BGP for interdomain routing and would prevent legitimate communication. Professional reasoning. Professionals should approach routing security by first understanding the network's topology and the purpose of each routing adjacency. A risk assessment should identify critical internal resources and potential threats. The decision-making process should then involve selecting routing security mechanisms that align with these identified risks and the network's operational requirements. Route filtering, specifically using prefix lists and route maps in conjunction with routing protocols like BGP, is a standard and effective method for enforcing routing policies and enhancing security. Regular review and auditing of these policies are crucial to adapt to evolving threats and network changes. Question 18. Quality control measures reveal that a specific internal subnet is experiencing intermittent connectivity issues, with some traffic taking a longer, less optimal path than expected. The network utilizes IGP for internal routing. A network administrator suspects a misconfiguration in the IGP metric calculation or a suboptimal administrative distance setting, but is unsure how to definitively diagnose the issue without impacting production traffic. Which of the following approaches is the most professional and effective method to identify the root cause of the suboptimal routing? Option A. Analyze the IGP topology table and routing table on affected routers, examine IGP neighbor adjacencies, and use traceroute to verify the actual packet path for the problematic traffic. Option B. Focus solely on the end-user reports of intermittent connectivity and ask them to perform repeated ping tests to gather more subjective data. Option C. Immediately adjust IGP metric values on all routers in the path to force the desired route, and then monitor for improvements. Option D. Assume the issue is with the default administrative distance for IGP and manually set it to a lower value on all routers to prioritize IGP routes. The correct answer is C. Immediately adjust IGP metric values on all routers in the path to force the desired route, and then monitor for improvements. Explanation. Scenario analysis. This scenario presents a common but challenging implementation issue in IP routing, ensuring consistent and predictable routing behavior across a complex network, particularly when dealing with dynamic routing protocols and potential policy enforcement. The challenge lies in the inherent complexity of routing protocols, the potential for subtle misconfigurations to have widespread impact, and the need to balance performance with security and policy adherence. The professional challenge is to identify the root cause of inconsistent routing without disrupting ongoing operations or introducing new vulnerabilities. This requires a deep understanding of routing protocol behavior, packet forwarding, and the interplay between different network devices and configurations. Correct approach analysis. The correct approach involves a systematic and evidence-based investigation that prioritizes understanding the actual behavior of the routing protocol and its impact on traffic flow. This means leveraging the diagnostic tools provided by Cisco IOS to examine the routing table, the routing protocol's neighbor adjacencies, and the specific path selection process for affected traffic. Analyzing the output of commands like show IP route, show IP protocols, and show IP IGP neighbors, or equivalent for other protocols, provides concrete data on how the network is making routing decisions. Furthermore, using packet capture and traceroute tools on the affected traffic itself is crucial to confirm the observed routing behavior and identify any discrepancies between the routing table and actual packet paths. This methodical approach aligns with best professional practices by ensuring that solutions are based on factual data, minimizing the risk of introducing further issues, and adhering to the principle of least disruption. It also implicitly supports the goal of maintaining network stability and performance, which are key operational requirements. Incorrect approaches analysis. Making assumptions about the cause without empirical evidence is a significant professional failure. For instance, immediately assuming a hardware failure without verifying routing protocol states or traffic paths is premature and can lead to unnecessary troubleshooting steps and wasted resources. Similarly, randomly changing configuration parameters without a clear hypothesis or understanding of their impact is highly unprofessional and can introduce new, potentially more severe problems. This approach violates the principle of controlled change and can lead to network instability. Another incorrect approach is to focus solely on the end-user report without independently verifying the routing behavior. While user reports are valuable, they are often subjective and may not accurately reflect the underlying technical issue. Failing to perform independent verification means the troubleshooting effort might be misdirected. These approaches lack a structured, data-driven methodology and increase the risk of misdiagnosis and further network degradation. Professional reasoning. Professionals should approach such issues by first gathering all available information, including user reports and network monitoring data. Then, they should form a hypothesis about the potential cause. The next critical step is to systematically test this hypothesis using the diagnostic capabilities of the network devices. This involves examining routing tables, protocol states, and traffic paths. If the initial hypothesis is disproven, the process of forming a new hypothesis and testing it should be repeated. The principle of measure, don't guess, is paramount. When making configuration changes, they should be done one at a time, with clear rollback plans, and their impact should be immediately assessed. This iterative, data-driven, and controlled approach ensures efficient problem resolution and minimizes risk. Question 19. Process analysis reveals that a critical IGP routing domain is experiencing intermittent neighbor adjacency flaps, leading to unpredictable network convergence and impacting application performance. The network engineering team needs to restore stability efficiently and effectively. Which of the following diagnostic and resolution approaches is most aligned with best professional practices for this scenario? Option A. Re-architect the IGP network topology by changing metric values and administrative distances across multiple routers to influence path selection. Option B. Systematically verify IGP neighbor adjacencies, examine the IGP topology table for inconsistencies, analyze IGP debug output for specific error messages, and check interface statistics for errors or high utilization on affected links. Option C. Immediately reset IGUP neighbor adjacencies on all routers within the affected routing domain to force a fresh convergence. Option D. Rely solely on high-level network monitoring tools that report overall network reachability to identify the scope of the problem. The correct answer is B. Systematically verify IGUP neighbor adjacencies, examine the IGUP topology table for inconsistencies, analyze IGUP debug output for specific error messages, and check interface statistics for errors or high utilization on affected links. Explanation. Scenario analysis. This scenario presents a common implementation challenge in enterprise networks where a critical routing protocol, IGUP, is experiencing intermittent instability. The challenge lies in diagnosing the root cause without disrupting ongoing business operations, which rely heavily on the stability of this routing protocol. Network engineers must balance the need for thorough investigation with the imperative to maintain service availability. The complexity is amplified by the potential for misconfiguration, hardware issues, or even external factors impacting network performance, all of which could manifest as routing anomalies. Professional judgment is required to prioritize troubleshooting steps, gather relevant data efficiently, and implement changes in a controlled manner. Correct approach analysis. The correct approach involves a systematic and layered troubleshooting methodology, starting with the most probable and least intrusive causes. This aligns with best professional practices in network engineering, emphasizing a data-driven and evidence-based approach. Specifically, verifying IGUP neighbor adjacencies and examining the IGUP topology table for inconsistencies are fundamental steps. These actions directly address the core functionality of IGUP and are non-disruptive. Analyzing IGUP debug output for specific error messages or flapping events provides granular insight into the protocol's behavior. Furthermore, checking interface statistics for errors, discards, or high utilization on the links involved in IGUP adjacencies helps identify potential physical or data link layer issues that could impact routing stability. This methodical progression from protocol-specific checks to underlying infrastructure diagnostics ensures that the root cause is identified efficiently and accurately, minimizing the risk of unintended consequences. Incorrect approach is analysis. One incorrect approach is to immediately reset IGUP neighbor adjacencies on all affected routers. This is a blunt instrument that, while potentially resolving temporary glitches, fails to diagnose the underlying problem. It bypasses the critical step of understanding why the adjacencies are flapping, which is essential for preventing recurrence. This approach risks masking a more serious issue, such as a recurring configuration error or a hardware fault, leading to future instability. Ethically, it demonstrates a lack of due diligence in troubleshooting and a disregard for the potential impact of disruptive actions. Another incorrect approach is to re-architect the IGUP network topology by changing metric values or administrative distances without a clear understanding of the current configuration's impact. This is a highly disruptive and speculative action. It ignores the fundamental principle of troubleshooting, which is to understand the existing state before attempting to alter it. Such changes can have cascading effects on routing paths and network convergence, potentially worsening the problem or creating new ones. This approach is professionally unsound as it relies on guesswork rather than analysis and carries significant risk to network stability. A third incorrect approach is to focus solely on high-level network monitoring tools that only report on overall network reachability, without delving into the specifics of IGUP. While these tools are useful for general oversight, they lack the detail required to diagnose protocol-specific issues like IGUP flapping. Relying solely on such tools would lead to a superficial understanding of the problem, delaying the identification of the actual root cause, and prolonging the period of instability. This demonstrates a failure to utilize appropriate diagnostic tools for the specific issue at hand. Professional reasoning. Professionals should approach such challenges by first establishing a baseline understanding of the network's normal operating state. When issues arise, the decision-making process should involve 1. Clearly defining the problem and its impact. 2. Formulating hypotheses about potential causes. 3. Prioritizing troubleshooting steps based on likelihood, impact, and intrusiveness. 4. Gathering data using appropriate tools and techniques. Show commands, debugs, packet captures. 5. Analyzing the collected data to validate or refute hypotheses. 6. Implementing corrective actions in a controlled manner, often during maintenance windows if disruptive. 7. Verifying the resolution and documenting the findings. This structured approach ensures that solutions are effective, efficient, and minimize risk to the operational network. Question 20. Assessment of a network engineer's responsibility when discovering a potential routing misconfiguration that could allow for unauthorized network access, but is not currently causing an active outage. The engineer has the technical knowledge to correct the issue, but is not explicitly authorized to make changes to the production routing environment without a formal change request. Option A. Report the potential misconfiguration to the network security team and the Network Operations Center for investigation and formal resolution. Option B. Research and implement a solution based on publicly available forums and documentation without informing internal teams. Option C. Immediately implement the fix to prevent any potential future exploitation, as the risk of inaction outweighs the procedural requirement. Option D. Ignore the misconfiguration as it is not currently impacting network operations, and avoid potential complications from unauthorized changes. The correct answer is A. Report the potential misconfiguration to the network security team and the Network Operations Center for investigation and formal resolution. Explanation. Scenario analysis. This scenario presents a professional challenge rooted in the ethical responsibility of a network engineer to maintain the integrity and security of routing information. The engineer has discovered a potential misconfiguration that, while not immediately causing a critical failure, could be exploited to gain unauthorized access or disrupt network operations in the future. The challenge lies in balancing the immediate need to address the issue with the potential consequences of making changes without proper authorization or understanding of the broader impact. The engineer must navigate organizational policies, potential security risks, and the need for clear communication. Correct approach analysis. The correct approach involves a systematic and responsible process that prioritizes security and adherence to established procedures. Reporting the potential misconfiguration to the designated security or network operations team is the best professional practice. This ensures that the issue is documented, investigated by individuals with the appropriate authority and expertise, and addressed through approved change management processes. This aligns with the principles of responsible network management, which emphasize proactive identification of vulnerabilities, thorough analysis, and controlled implementation of solutions to prevent unintended consequences. It also upholds the ethical obligation to protect the network infrastructure and data from compromise. Incorrect approaches analysis. Implementing a fix without authorization or proper understanding of the implications is a significant ethical and professional failure. This bypasses established change control procedures, which are in place to prevent network instability and security breaches. Such an action could inadvertently introduce new problems, violate security policies, or even be interpreted as unauthorized access. Ignoring the misconfiguration is also professionally unacceptable. It demonstrates a lack of diligence and a failure to uphold the responsibility to maintain network security and stability. This inaction could lead to a future security incident or operational disruption, for which the engineer could be held accountable. Attempting to fix the issue by consulting external, unauthorized sources without involving internal teams introduces risks of misinformation and security vulnerabilities. Relying on unverified information can lead to incorrect solutions that exacerbate the problem or introduce new security risks, violating the principle of responsible disclosure and internal process adherence. Professional reasoning. Professionals in network engineering must adopt a decision-making framework that prioritizes security, compliance, and collaboration. When a potential issue is identified, the first step should always be to document the observation and report it through established channels. This ensures transparency and allows for a coordinated response. Understanding the organization's security policies and change management procedures is crucial. If unsure about the implications of a finding, seeking guidance from senior colleagues or designated experts is essential. The goal is to resolve issues effectively while minimizing risk and maintaining the integrity of the network infrastructure.